Welcome back. Here we are with Chemistry of Life Part 2, and we're going to pick up once again where we left off with those 4 organic molecules. We're going to talk today about lipids, but before I even get there, we're going to talk about the fact that they are, once again, organic molecules, which means they are not just molecules of life, but based on carbon. So there's that element carbon. And why is carbon so unique? Why is carbon so important to life? Well, it's because I have to say it's the superstar in the periodic table, because carbon has, well, let's think about its number for a second. Its atomic number is 6. Atomic mass is about 12. Okay, so here's the atomic number, which means it has 6 protons. Well, okay, now remember, inner ring of valence electrons, it'll only hold 2. So I'm going to set 1 here and 1 here. And then the next ring outside of that would like to hold 8. But since I have 2 here, I will have 1, 2, 3, 4. Sorry for my crude drawing. What's the point here? Carbon would love to have 4 other electrons in this outer shell. So it won't be really easy to give away all 4 of these, so that won't work as far as ionization. But what it can do is it can share very well. And what it can do is it can share in 4 different directions. So we kind of have to think a little bit in 3D. So think of kind of my little drawing here coming out of the screen. Okay, and this one, I'm going to kind of go more like this into the screen. And carbon is really good at either bonding another carbon, because once again their electronegativities are about the same, or bonding hydrogens, same thing. Well, electronegativities, 2 carbons would be identical, but hydrogen and carbon are about the same. And so what we end up getting here is an example of a carbon molecule. It's methane. 1 carbon with hydrogens all around it, 1 coming out of the screen, 1 going into the screen, and 2 that are flush with the screen right here. And they're all about 109, I believe, 0.5 degrees apart. What's the point? These carbon atoms are really good at making chains and these really complex structures with themselves, and hydrogen especially, along with other atoms as well. But what we're going to see is that these carbon atoms are really good at making chains, and that's what we're going to talk about today, are lipids, which many times are simply just chains of these carbons hooked together. And if I look at this, I know that each one of these carbon can bond 4 times, so each one of them in the middle here will have 2 hydrogens coming off. And once again, you'd have to think a little bit 3-dimensionally here. Some are going into the screen and some are going out of the screen. So let's get into those lipids. So what are lipids? Well, first of all, they do not dissolve in water. So there's that magic word we talked about last time that I said is going to be very, very important. Hydrophobic, fearing water, right? They fear water. Which once again makes sense, because they are hydrophobic, they are nonpolar. The reason they are hydrophobic is because they are nonpolar. There's no partial charges in their covalent bonds. They share the electrons evenly. They are used as energy molecules. Well, wait a minute, why would that be? Why are lipids often used for energy molecules? Well, remember how I said we have these carbon-carbon bonds? Whenever we have 2 atoms coming together at a point right here to share electrons, that bond, there's energy stored in that bond. So what we'll find out is cells will break apart these bonds, these carbon-carbon bonds at times, and by breaking that bond, it will release energy. And we can use that energy to maybe form other bonds, to form new molecules, or maybe do mechanical work, or maybe actually increase heat. So this is the main way that we're going to be getting energy. Also, they're found in cell membranes. Well, we briefly mentioned that last time. We talked about that concept of phospholipid bilayer. We're going to get much more into it today. So every cell in the body, every cell period actually in life, okay, will have a cell membrane that's made up of these phospholipid bilayers. And then lastly, they're found as fats and oils, as well as phospholipids and steroids. So just this quick list, we're going to see, okay, fats and oils, we think of food, right, as an example. So once again, why do we have food? For energy. Phospholipids, we should be thinking more or less membranes, cell membranes. And steroids, well, lots of things, but we could think maybe hormones. There's more under each one of these categories, but those are kind of, once again, the big players. Let's keep moving here. Let's talk first about those fats and those oils and how are they different. So once again, being a biology class and a fitness degree program, fats and oils should be probably pretty familiar with you, or you should be familiar with it, I should say. Fats are usually of animal origin versus oils are typically of plant origin. Fats, here's the other big difference, are solid at room temperature, that's what makes it a fat, versus oils are liquid at room temperature. Fats function in long-term energy storage, insulation from heat loss, so yes, we use fat as an insulator, and cushioning for organs. All this is good stuff so far. Now, from a molecular standpoint, what's the difference between these two? We're going to find out they are still simply chains of carbons, it's just the chains are arranged slightly differently. So once again, here are our fats over here on the left. We tend to think, once again, more animal origin, whether it be meat or cheese or eggs, what have you. If it had eyes or a mother, I once heard an RD say it's a fat. And oils typically are from plant origin. So now, how do we get these oils and fats? Okay, well, first of all, we have what's called a fatty acid. And here's another way of lining up those carbons with those hydrogens around it like I already described. Once again, I'm going to look at this carbon right here. It's bonded 4 different directions. It shares electrons this way, this way, this way, and this way. So it's bonded to 2 other carbons and 2 other hydrogens. It's got its complete octet. It's happy, and you can see that all the way down. And it's just a chain of carbons. And then over here, we haven't gone over this. Here we have a carbon still bonded here. We have a double bond, so it's sharing not just 2, but sharing 4 electrons with this oxygen, and a single bond with this hydroxyl group. This is what's known as a carboxylic acid. Now, honestly, I don't care too much if you remember that right now. That's not as important, okay? There's a few things of importance here. The carboxylic acid, you can learn more about that in chemistry and organic chemistry. Just stick with me right here. We have these fatty acids that we're going to take into our diet, from our diet, okay? And we can imagine how this side would be very non-polar, right? Non-polar over here, they share evenly, but we got kind of a polarity thing going on over here. There's an uneven sharing of electrons over here. So it's kind of that amphipathic type of concept again. But really what's going to happen when we take in a fatty acid from our food, we have this hydroxyl group right here, that OH I just mentioned. And then over here we have a whole other molecule you've probably heard of before. It's glycerol. We're going to find out glycerol is similar to a carbohydrate. Sometimes it almost gets classified as a carbohydrate, even though strictly speaking it's not really. It's close. Glycerol is a lot like a small carbohydrate, and it has 3 carbons, 1, 2, 3, and each one of those carbons not only has the hydrogens attached to it, just like these guys, but each one of them has a hydroxyl group, an OH. And what will happen is the hydrogen over here from this OH is going to bond with the hydroxyl group over here, and what's going to happen? Water is going to leave. Right? And we're going to get a bond. This oxygen is now going to take the place of this oxygen. Oh, let's look over here all the way. I'm going to go all the way over here. And here, this carbon, I'm going to just put the name of this carbon 1. Here's carbon 1 over here. And we can see here's that original oxygen bonded to carbon 2 over here. And that, once again, is a dehydration reaction. We took away water and we linked this fatty acid right here to this end of glycerol. And remember, dehydration reactions, how we start building up those chains and polymers and what have you. Larger molecules from smaller precursors. Over here's our smaller precursors. Over here's our larger molecule. Basically, we do that 3 times and we get a fat molecule, a triglyceride. I'm sure you've heard of triglycerides before. We get a fat molecule and 3 waters that have come off of it, because I got water coming off of this first group, second group, and third group. So once again, a dehydration reaction over here, losing water to build the larger fat molecule, or we can break it apart into the individual fatty acids through hydrolysis by adding water. Right? So once again, we build through dehydration by taking water away, and we break apart by adding water back to it. And there are enzymes that are going to help these reactions along, so it's more than just randomly adding water to a beaker full of fatty acids and glycerol. There's more to it than that. But basically, these are the concepts I need you to get. This is how we get a triglyceride, a fat molecule. But wait, there's more. I also said, how are we going to know the difference between a fat and an oil? Basically, they're the same as far as this reaction I'm showing you right now. But a fat is going to be primarily these type of lipids over here, where all these carbons are single bonds. Now, do you see down here in this last one, though, we have a double bond here. So these carbons, rather than just sharing 2 electrons, are sharing 4. So we don't need the additional H's down here. That's why there's like this gap down here. So this carbon wants to share 4 electrons. 1, 2, 3, 4. It's happy. Same on this side. So in a sense, this one, and compared to these guys, are missing 2 hydrogens. Well, what's that going to do to the molecule, and why would it be different? Well, fats that are solid at room temperature are going to be primarily here. They're saturated with hydrogens. So you've heard the term saturated fat. What that means is you're saturated with hydrogens. Every single carbon is filled with hydrogens. So the saturated with hydrogens. An oil will have more of this, unsaturated. It's not saturated with hydrogens. It doesn't have hydrogens on every single carbon. Some are 2 carbons on each one of these middle ones. Some are double bonded. We've got a double bond. So this is unsaturated here. We put unsat. Okay? Well, that might still be a little confusing. Who cares? What's the difference, and why would one be solid at room temperature while the other one is liquid? Well, saturated fats, if you can imagine like a little chain, it's not a very good drawing, can line up really well and stack on top of each other. And so once again, just a whole bunch of kinks, and they just line up really nicely, and they can pack really tight, and that's why they're solid at room temperature. But what happens with this double bond is it actually creates a kink. So imagine double bond. So I have a whole bunch of that, a whole bunch of kind of chains with a kink in it. They don't stack up nearly as well. So they are separated more, and so hence an unsaturated would be liquid. This is where your oils are going to be. While the ones that aren't kinked are going to be solid. These are going to be more your fats. Now let's take this to nutrition. Now the reason we want to watch those saturated fats right here are because they are solid and they are hydrophobic. So you put them in your system and they like to clump up together. And for lack of a better term, I'm going to say they're going to clog up the works. While unsaturated oils, well, they are still hydrophobic, but they won't clump up together like a saturated fat will. Now notice over here we also have trans fats. Now, what are trans fats? Remember I talked about the kink in the chain for unsaturated. I'm going to draw a little better this time. Here is my kink in the chain for a unsaturated fat. And notice that the kink goes in the same direction. That kink is called cis. A cis bond, a cis double bond right here. Okay? Well, that's how oils are found typically in nature. Well, you know, mankind, we think we're so darn smart. What we're going to do is we're going to take this healthier fat that's actually really good for us. We're going to need unsaturated fats. They're really important in our diet for everything from heart health to brain health. We're going to heat up these healthy fats, and we're going to flip this double bond so that instead, let's see if I have enough room here, the kink goes like this. It kind of goes kink and then kind of in the same direction. That's a trans double bond. Hence we get the term trans fatty acid. Well, what we've discovered is that these trans fatty acids that start off with the best idea, we want to take a healthy fat and make it a little bit more like a saturated fat. We're going to heat them up through this process called hydrogenation, so we can make Twinkies last to millennia. So it increases shelf life. Well, the health detriments to saturated fat, well, there's a lot of them. Heart disease, and well, the list is pretty long. Trans fats are even worse. So as of, I think it was about 2006 or so, labels had to start including trans fats as well as saturated fats, because these are the two fats that we want to minimize as much as possible. I'm going to call them bad fats. You know, I hate using the term bad for anything. There's always a cause for something. So let's go back over here. All right. So these are kind of out of your book. You know, the recommendation for total amount of fat for a 2,000 calorie diet is 65 grams. That's kind of the general rule of thumb. Obviously, depending on the person and their goals, that could change. But for the general public, that's what we're shooting for. We want to make sure that we understand about servings and the percent daily value, what have you. Once again, the key here, though, is the really unhealthy fats are these trans fats, which you're going to find, you know, in a lot of fried foods, especially, or foods that, once again, are intended to have a long shelf life. So let's go ahead and watch this little video from the publisher, a little bit more about anatomy of a food label.
Here is a typical nutrition facts panel from a food label. The label information is standardized so that consumers can compare nutritional values of similar foods. The basic information is serving size, servings per container, calories per serving, and calories from fat per serving. Compositional information is listed for total saturated and trans fat, cholesterol, sodium, total carbohydrate, dietary fiber and simple sugars, and protein. The percent of established daily values are also listed for each component except protein and trans fat. Percent daily values are calculated on the basis of both a 2,000 and a 2,500 calorie per day diet. Percent daily values for vitamin A, vitamin C, calcium, and iron are also displayed. The percentages of daily values are calculated from the established daily values for these components. The established daily values are shown on the label for both the 2,000 and 2,500 calorie per day diets. Compare the established daily value for total fat for the 2,000 and 2,500 calorie diets. The established daily value is based on the recommendation that the total fat be no more than 30% of total calories. 30% of 2,000 is 600 calories. 600 calories divided by 9 calories per gram equals 66.6 grams of fat. That is adjusted down to 65 for the purposes of the label. 30% of 2,500 is 750 calories. 750 calories divided by 9 calories per gram equals 83.3 grams. This is adjusted down to 80. These calculations are repeated for saturated fat, carbohydrate, and dietary fiber. Cholesterol and sodium recommendations are upper limits for intake and independent of the calorie intake. Calories per gram for fat, carbohydrate, and protein are often included. From the weight of total fat on the label, you can check the percent daily value that the label displayed.
Okay, well, now that we talked about fats and oils, let's go ahead and talk about those steroids. Now, what are steroids? Well, they're still lipids, right? They're still lipids. And they have a very different look because they're actually based around the molecule of cholesterol. And once again, we tend to think often that cholesterol being a bad thing. Well, cholesterol, once again, is a very important molecule in the body. It's very important in cell membranes for the fluidity of cell membranes. We'll get back to that. But it is also the precursor for these steroid hormones. We take cholesterol and modify it in order to get both testosterone and estrogen. And you can see it's actually 4 fused carbon rings. So we're seeing these rings, but what are these rings made up of? They're made up, again, of carbon. So each one of these points in the ring is a carbon. So whenever you see a ring structure like that, unless otherwise notated, whoop, by like what I accidentally did right there. Let me change that. I'll say notated by another atom. So I don't know why I quite did that. Unless otherwise notated, it's going to be a carbon there. So whenever you see a ring or even just a kink over here, any of these where it doesn't otherwise say so, where it's just a kind of this little kink in the chain, all of these are carbons. Now let's get back to that phospholipid bilayer that we talked about last week. What's it made out of? Well, we still have that glycerol that I introduced you, that almost carbohydrate. We have 2 lipids, and here is that polar phosphate group, which is, when it phosphate is PO4 minus 1. It's that phosphate, it's what's called a polyatomic ion. This phosphate, when we hook it onto these other 3 things here, 2 lipids and the glycerol, it's going to create one end of it that's highly hydrophilic, loves water, while the lipid side, well, once again, highly hydrophobic. So what does this phospholipid bilayer do? Like we said last time, it allows a cell to separate one side of the membrane from the other, 2 aqueous sides. And we have what's called semi-permeability, which allows migration of some molecules and atoms, but not others. For example, salt, sodium chloride, and water separate into their respective ions, sodium and chloride ions. However, they cannot pass the cell membrane because of the hydrogen bonding in water. Well, the water on one side wants to hold on to those ions, but furthermore, they're repelled by the hydrophilic lipid portion in the center of that phospholipid bilayer. It's the same with any other hydrophilic or polar molecule, like glucose cannot just diffuse across the membrane. Therefore, we have cells that can generate gradients of ions and molecules, separating them from the outside versus the inside of the cell. For example, the calcium, a very important ion, we're going to find out the calcium ion concentration is sometimes 1,000 times greater on the outside of cells versus the inside. Well, how do things get across if they cannot just simply diffuse and cross that layer? Well, sometimes there are what's called ion pumps. Now, what is an ion pump going to be made of? Well, we're going to find out it's going to be made of proteins that are embedded within the membrane, and they will actively pump ions or molecules from one side of the membrane to the other, either inside out or outside in. Now that actually takes fuel. It takes energy. For example, most of the energy in your brain is for ion pumps to ensure proper gradients, so your neurons, basically your nerve cells in your brain, are going to work properly. But there are also channels, specialized channels that allow passive diffusion. What we mean by that is just allows it to flow from one side to the other. So imagine like these donut holes that are specialized for certain molecules or ions that are going to allow certain things to bypass and just go in and out of the cell passively. And when I say passively, I mean no energy is required. However, it might have a gating mechanism. So imagine I have my phospholipid bilayer. So here are my, once again, my lipid ends and my lipid centers and my hydrophilic exteriors to this layer here. And we're going to call this the inside of the cell, and this is the outside. So this would be actually extracellular fluid out here. This would be intracellular. The cytosol fluid is the fluid in there. And there might be this protein that once again kind of acts like a giant donut hole here, if you will. Kind of draw it like that so you kind of, where only certain molecules can either go in or go out. And there might be a gating mechanism. So sometimes this channel is closed and sometimes it's open. Now it will take energy to open or close it, but once it's open, then everything can flow in and out passively. Let's take a look what some of this might look like. So here we have that phospholipid bilayer, the layer of our cells and our intracellular membranes, the makeup of our cell membranes, I should say. And once again, we see that at the core is this phospholipid area, right? And at different places, we might have little cholesterol molecules that are going to help everything be fluid. So this is not something rigid here. And we also have these big proteins. So like right over here, here's a protein channel. It's kind of cut down the middle. So once again, it's kind of like that donut where it's going to allow certain things to go either in or out. And I should have already mentioned, do you see here's cytoplasm, the inside of the cell. Here's the extracellular fluid. So once again, phospholipid bilayer with these proteins embedded throughout. And these proteins are going to do certain jobs within the membrane. It's going to keep certain things out, let other things in. It might allow movement within the cell. We're going to find out there's this cytoskeleton when we get to the cell structure here. These things coming off. They're going to allow movement of things inside, kind of create the infrastructure of the cell. We also have some carbohydrates coming off. My point being is, right here we're only looking at the membrane and we can already see that the membrane is very complex. That's point number one. Point number two, yes, it's primarily made up of this phospholipid bilayer, but embedded in the bilayer are all these proteins. And sometimes along with the protein, we're going to get some carbohydrates attached to it, but really a lot of proteins are going to be spanning here. And we're going to be talking about proteins in a couple of minutes, but we're going to find out these proteins are once again kind of the structural workhorses within your body. They actually do a lot of action. They're kind of like little machines within the body to get the job done. So lipids, the first one we're talking about as far as our big four organic molecules, they're great for energy. We saw that. That's why we eat fats and oils. They're highly compact energy. They're energetically dense, if you will. But also they are also used for structure. Specifically, we're going to see it a lot, but specifically in this phospholipid bilayer, which is the core of all cellular membranes. We're going to revisit once again this concept again and again of this phospholipid bilayer and what things can get across and what things can't. So don't worry, this lipid bilayer will come back for more later. Let's go ahead and move on to carbohydrates.